We're going to take a look at how to solve an open channel flow problem using a spreadsheet, and the example I have is using a trapezoidal channel, which is the more difficult one, but I want to point out first is that for a trapezoid, the area is the base, both bases, divided by 2 times the height. So let's go ahead and get started. I'm going to be making use of this. If you have a circle or a rectangular one, it's much easier in being able to find out what the area is, but I just want to point out this is the formula I'm going to be using. So what I already have is a open channel problem over here. Question is similar to what you have for your homework. It is a given ditch section has a flat bottom of 4 feet, which is over here, a 3-to-1 side slope, which is 3 horizontal and 1 vertical. The proposed channel has a slope of 0.58%, and the estimated 10-year design flow expected for this ditch is 200 cubic feet per second. And we're going to be using a friction factor of 0.03. So first question is, what is the estimated depth of the water for a 10-year flood? This is going to be the depth that's going to give us a 200 cubic feet per second flow, which is what this states right over here. Second one is, what is the estimated velocity of the water at the 10-year flood, which is going to be, okay, now I'm going to need to, with all the other conditions, what is the velocity in that channel? The next one over here is, if the project manager wants the flow to be less than 5 feet per second, that's the velocity, how low would the ditch slope need to be lowered to in order to obtain this velocity? Next one B is, what would the resulting depth be? And if the depth was desired to be below 3 feet, for the answer in D, what side slopes would be required? And then finally is, what is the resulting spread of the water? The spread of the water is going to be, whoops, I didn't need that. What I'm looking for, the spread of the water is going to be, what is the distance across over here for a specific depth of the water? So the spread of the water is the length across the top of the trapezoidal ditch or channel. So to get started, I've already filled these in, but I'm going to go over here and show you what the resulting equations are. So the first one is questions A and B with what is the estimated depth of the water at the 10-year flood, and what is the estimated velocity of the water at the 10-year flood. So I'm looking at over here as I first have where I constructed, I put in a cell. I have what is the bottom width. So I have 4 feet. I'm putting in here is my side slopes, which is a 3-to-1. My longitudinal slope is 0.058. Over here I have 0.58%. I put that all in. Now I have it highlighted here in yellow. That is going to be the cell I'm going to vary. That's going to be my depth of my water. And I have my channel roughness of 0.03, which is what I get from the statement of the problem. So what is the estimated depth at the 10-year flood? And what I have done now is here's all the information I'm going to need to solve this problem. These are the parameters I'm going to put in. So first off is for the spread of the water, which is going to be what is the length across the top of the channel, presuming a specific depth of the water. So over here I have that I have initially is A20. Cell A20 is the 4 foot across the bottom. So that brings me up over here. That's the spread attributed to the bottom over there. But for each foot of depth of the water, I'm going to have 3 more feet, or 3 times that is going to be resulting. So if I go up a foot, I go over 3, so I'm going to have to multiply that by 3. So what I have for my result over here is I have there, right over here is A20 is going to be the cell for the bottom width. That next one is I have is a factor of 2 because I have spread the water is going to be one side over here and then the resulting other side. And I have A23, which is going to be the depth of the water that I have. So that is going to be this over here. But now every time I go over a foot, go a foot in depth, I come over 3 feet. So it's a ratio of 3 feet, which is going to be taking this cell over here. So when I look at the spread of the water, I have to account for that. So I have A21. So I have my side slope times the depth times 2 is going to be added to the width of the bottom of the channel. That's going to give me my spread of the water across the top. So this is merely a copy of this particular cell is the depth of the water. So now I know what, in order to be able to figure out for my trapezoid is I now have one base, the other base. So I go back to my area calculation over here. I have A and B. So now I have both A and B, which is the spread of the water and the base of that particular trapezoid. So I have those two items. Now if I'm looking at the area, I'm going to have 1/2, and I've got A20, which is now going to be the bottom width. And I have A26, which is the spread of the water. Those are the two bases of my trapezoid. So here's the half base 1, base 2 times the depth of the water is going to give me my area of flow. So that's how I come up with this one over here, just based upon this information that I put into the spreadsheet. My wetted perimeter is going to be the base, and then I have to be able to figure out what the length is of these sides based upon how deep the water is. So what I'm going to do is look for my wetted perimeter. I have A20, which is the bottom of it. Now I'm going to have to figure out what this distance is over here. So now I'm coming back. I'm going to take a look at, I have two of those. I'm going to take a squared plus b squared equals c squared. So I'm taking the square root of taking the depth and then 3 times the depth and squaring it, which is going to give me the hypotenuse of this triangle. So I'm coming over here. Here's my depth of my water. Here's taking that by the side slope, which is going to be 3. So when I come over here, I have A23, which is the depth of the water. Then I have A21, which is the side slope. And then I have A23 again. So I'm just taking these two items and squaring them. So I have a squared plus b squared. I'm taking the square root of those in this function over here. And what that allows me to do is now come up with the wetted perimeter. So now I have my hydraulic radius is the area of flow divided by the wetted perimeter. So now I'm just taking A29 divided by A30, which are these two items, and that gives me my hydraulic radius. So now I have expressed all the items I need in order to be able to figure out my flow in the parameters that I've been given. So now I can come back over here, and first thing I need to do is, what is the estimated depth of the water for 10-year flood? And what I needed to do is just by trial and error over here, as this says that I need to vary the depth until you obtain a 200 cubic feet per second at the end, which I've already kind of done. But now if I take this and I make an initial guess of 3.5, I could put that in, and I will see that, okay, I have 298. Obviously, that's not going, more flow than I needed, so I'm going to actually size that channel, that ditch, so I get the 200 cubic feet per second. So now I take another guess. I'm going to say, oh, let's drop it down to 3. And oh, now I'm at 209.9, so I'm getting closer. I come in 2.96. I can put that in, and I'm getting even closer. So let me try 2.91. And that's a little bit too low. 2.93. Getting closer. 2.94. And a little bit over. 2.9365. See if what that does for me. And that's what I had before. So I've just been playing around with the depth of the water because I have everything else locked in here based on the problem. And now I've got that as 199.987. That's pretty close. You can do it a little bit further if you wanted. But now that I've done that, I see that my velocity is 5.31. So I've done over here is, here's my Manning's formula, is 1.49 over A24, which is my channel roughness. Then come over here is going to be my hydraulic radius, which is A31, that cell right here. And that's raised to the 2/3 power. Again, I put this in parentheses so that divides 2 and 3 and gives me the 0.667 that I need in order to do that part of the equation. And the last part of it is I need to have my slope, longitudinal slope, to the 1/2 power square root of it. So A22 is my longitudinal slope. And that's gone to the 1/2 power, so that's how I get that one. And down over here, now I'm just taking the area of flow, which is cell A33, which is, sorry, that's the velocity, times A29, which is my area of flow. So I have my velocity and then the area that the flow is going through. And that gives me my volumetric flow in cubic feet per second. So that's how I get a trial and error solution for the first part of it. Second part is, now I'm looking at, if the project manager wants the flow to be less than 5 feet per second, how low, I need to change this, how low would the ditch slope need to be lowered to get this velocity? So I'm just going to, I took this and I copied it all back over, so I could just do a copy and paste over here, because this is all just doing the same thing. But now instead is that I'm now changing 2 items over here. I have these highlighted in yellow because these are the ones I'm going to vary. What I do have again is the bottom width, the side slopes. This is what I'm going to be changing in order to get my flow down below 5 feet per second. And then later on is that I'm going to have to vary the depth to obtain 200 cubic feet per second. I still just need the channel to carry the flow from a 10-year design storm. This stays the same. So I was just playing around with this beforehand just to get this information. So what I do first is, if I, looking at this, I want to get down below 5, which is what I did over here. I could have started out first as, okay, put 004, and, oh, nope, that's not going to be what I need because that's much too low for the velocity. Again, I just copied these over. Now I still have my velocity and volumetric flow. So what I did is I just played around with it till I came up with 0049, which gives my flow down over here. And now if I look at 3.1 is the depth of the water that I had, that my velocity is going to depend a little bit upon the depth of the water, because that changes some of the parameters over here. And it gives me a little bit different velocity, but then I also see where now I have my flow is a little bit over the 200 cubic feet per second that I need. So what I'm going to have to do on this one over here is continue to just play around with the two of these to balance them out to where I get to a 200 cubic feet per second of flow and right around 5 feet per second, just a little bit lower than that, just by playing with these two. That's why they're highlighted in yellow. Those are the items that I'm going to vary. And again, my formulas are exactly the same over here as they are over here, except that now I've got the parameters I'm looking at are out of here. So this is my solution for A and B. I've just copied these over to this column over here in order to be able to solve for the question portions on C and D that I need, which is I want to be less than 5 feet per second, and what would the slope need to be lowered to obtain that. And then on D is what would the resulting depth be in C. So this is going to get my flow down below the 5 feet per second. This is the depth I need in order to get down to the 200 cubic feet per second of flow. The last items that I need to do to solve this are going to be is, if the depth were desired to be below 3 feet for answer in D, what side slopes would be required, and what would the resulting spread of the water. So now I'm going to come over here, and I've copied these again. Same information. I have my bottom depth of my channel. I have, this is now I'm going to be varying my side slopes. I leave my longitudinal slope as a 0.0049 that I got from the answer in C and D. My depth of my water I'm leaving at 3 because over here it says that I want it to be below 3 feet. So I put that in as my depth of my water. And what I'm going to be doing now is playing with this in order to balance out the 5 feet per second and 200 cubic feet per second of flow and velocity. So now my problem would be over here is just to go ahead and start to change that, because it's looking at what side slopes would be required. And I could have gone to, this really is looking at 4. I do 4. Well, that doesn't give me what I want, because what I'm looking for is I want to keep the depth below 3 feet, but I just need to have 200 cubic feet per second. So that's a little bit too high. And come over here to 3.1, and I'm getting close. So I have 197. I could probably make my slide slopes a little bit more than 3.1, and 3.15, 3.16. I'm just varying these to get to, so I've got 3.165. If I put that in there, whoops. And I'm pretty close. If I have 3.165 as my side slopes, I have it at the 200 cubic feet per second. My velocity is just a little bit below 5. So the question here is, what depth, in order to keep the depth at 3 feet or below, what side slopes will be required? And I've done that here. The next item that I need here is, what is the resulting spread of the water? And I've just carried over the same information I had previously. So the spread of my water is 22.99. So that is the bottom width right over here. If I hit F2, it tells me that all went in here. I have this is my bottom width, and then I'm looking at 2 times my side slopes times the depth of the water is going to give me the extra spread of water on each side over here added to the width of the channel, and now I've solved my problem. So hopefully that gives you an idea of what's going on here. Again, how I started was I just entered all this information in. So this is what I'm going to be playing with, are the items that are highlighted in yellow. My spread of the water is the bottom depth. I have the side slope times the depth of the water. I multiply that by 2 to get the 2 sides of my channel. The depth of my water is just carried over from over here. And my area in square feet is going to be looking back at, here's my area of my trapezoid. So that is 1/2. Here's my 2 bases. A 20 is, again, the bottom width of the channel. This is the spread of it. And times the height of the trapezoid, or the depth of the water, gives me my area of flow. My wetted perimeter, again, is the bottom of the channel. Then I have 2 sides over here. I need to calculate what the length of this is for that depth of water. And so I'm coming over here, I have the square root of a squared, which is the depth of the water, plus b squared, which is the side slopes, times the depth of the water. That squared, those 2 items are added together, and I have the square root of that. That's going to give me the length over on these both sides. So now I have the wetted perimeter. I divide these 2 numbers right here, and I get my hydraulic radius. This is just plugging in Manning's formula, which is 1.49 over N, which is the friction factor. Then I have my hydraulic radius, which I just figured out right over here. And that is to the 2/3 power. And then the last term I have over here is the slope to the 1/2 power. But again, is that I have this 2 divided by 3, I have parentheses around it so that it performs the function first of dividing 2 by 3. So I have it, the hydraulic radius to the 2/3 power. And same thing over here. So it's the 1/2 power. If you don't take into account the order of operations, then your math will be wrong when you do the calculation. So these are all how I got this information over here. This one is just taking this velocity times the area of flow, and that's how we've been able to solve this problem. Hopefully that helps out. It's a lot easier to do this with a spreadsheet than to try and do it on a calculator or by hand. This allows you, when you have the items picked out over here that are highlighted in yellow, you can just vary those to get the answer that you need to match all of the parameters that are called out for in the problem.